Hello friends, welcome to the another session. We have seen that no real gas obeys the gas laws perfectly. At ordinary temperatures and pressures, the deviation is small, but at high pressures and low temperatures, the deviations are very large. We have also seen that while deriving perfect gas laws on the basis of kinetic theory of gases, following assumptions have been made. The first is, but which do not hold true in the case of real gases. But the first one is the molecules are mass points having no finite volume. And second one, there is no attraction or repulsion between the molecules. The experiments of Andrews on CO2 and those of Joule-Thomson's liquefaction of gases have clearly shown that there exists a force of attraction between the molecules of gas. Through this force of attraction in gases is much less than that in case of liquids, yet it is significant. Van der Waals modified the perfect gas equation. So that is PV is equal to RT. By applying the corrections, the first one is the finite size of the molecules, and second, that is the intermolecular attraction, and obtain the equation for real gases. So today we are discussing why the PV is equal to RT goes to modified. So today we are discussing Van der Waals equation of state. Why the modification of gas is required. The perfect gas equation PV is equal to RT is not obeyed by real gases, particularly at high pressures and low temperature. At ordinary temperatures and pressures, the deviation is small, but at a high pressure and low temperature, the deviation are very large. In the derivation of the perfect gas equation, on the basis of kinetic theory of gases, as we already discussed the two assumptions, that is the size of molecule of the gas is negligible and the force of intermolecular attractions are absent. But in actual practice, at a high pressure, the size of the molecule of the gas becomes significant and cannot be neglected. In comparison with the volume of the gas, also at a high pressure, the molecules come closer and the force of molecular attractions are appreciable. Hence, the perfect gas equation needs to modification. In 1879, Van der Waals modified the perfect gas equation PV is equal to RT by applying the corrections for intermolecular force of attraction and finite size of molecules. So the first one is the correction due to the intermolecular forces. Consider a molecule of gas well inside the vessel, that is the BE and CD. It is attracted by another molecules in all directions with the same force, and the net force acting on it is 0. But when it strikes the wall of the vessel, here this molecules strikes to this wall of this side. So that takes the position A dash. It is pulled back by other molecules. Its velocity and hence momentum with which it will strike the wall would be less than the momentum with which it will strike in the absence of force of attraction. The reduction in momentum results in decrease of pressure, or we can say that the observed pressure of the gas is less than the actual pressure. So the correction pressure P, here I am representing the pressure small p for correction pressure. It depends upon the number of molecules striking a unit area per unit time of the walls of the container and the resultant inward pull of cohesion on each of the striking molecules. So each of these factors is proportional to the density of the gas. So the correction for pressure, the small p is the referred as a pressure, correction pressure. So P is directly proportional to the square of the density, is inversely proportional to 1 by V square. That is inversely proportional to V square. So P is equal to A by V square. Here A is the constant and V is the volume of the gas. So therefore the corrected or real pressure, what we say, the corrected or real pressure, that equals to capital P plus P is equal to P plus A by V square. So we just take here the correction of the small p with the real pressure P. So we get P plus A by V square. Here A by V square is nothing but P, that is the corrected pressure. So where P is observed the pressure, capital P is observed the pressure. Now second, that is the correction due to the finite size of the molecules. Again let us consider a molecule of A of a gas in a closed container having volume V, moving parallel to the, where we can say that in the chamber, that is the CD. Suppose the molecule strikes the face at the side of D of the container at B and come back. Let the distance between travel by the molecule is not 2r. So if we consider the motion of all the molecules in a container in this way, we find that the effective volume in which the molecules move is less than the total volume. Thus, when the pressure is increased, there is decrease not in the entire volume but a part of it, that is V minus B, where B is the volume of the portion which cannot be compressed. Here the B is the volume of the portion which cannot be compressed. So volume of B is called the co-volume of the gas. One can easily show that the co-volume of B is 4 times the actual volume occupied by the gas. So due to the finite size of the gas molecules, the actual space available for the movement of the molecules is less than the volume of the vessel. The molecules have the sphere of influence. This blue dotted line is a sphere of influence around them of radius 2r. ये दोनों का यहाँ से लेके क्योंकि when they collide with each other as the sphere of influence is set up. So the red lines, the two molecules are there. When they collide with each other, a sphere of influence is set up, and that diameter of the sphere of influence is twice of r. So within which no other molecules can penetrate. Let the molecules have a radius r, then its impact with a similar molecule of its sphere of influence of the radius equal to, that is the 2r, this one. Because when two molecules touch with each other, the distance between their center is twice of r. Let us fill the whole space of volume V of the container with n molecules of the gas one by one. When the second molecule of the gas is brought in the container, the available volume is V minus 8x. So here we are going to solve this. How V minus 8 is there? So first we know the r is the radius of each gas molecules. So as we know the volume of the molecule, that is x is equal to 4 by 3 by pi r cube. This is the volume of the molecules. Now the center of any two molecules can approach each other only by momentum, and that is with minimum distance of twice of r. The volume of space or the volume of sphere of influence of each molecule is S is equal to 4 by 3 pi twice of r whole cube. This is the center of any two molecules, or so that they are penetrate with each other. So the volume of sphere of influence of each molecule is 4 by 3 pi twice of r whole cube. So that's equal to 8, just rearranging 4 by 3 pi r cube. So S is equal to, that is the sphere of influence of each molecule is equal to 8x. Sometimes it is x referred as a volume, that is the average volume of the molecules. Let us fill the whole space of molecule V with n molecules one by one. एक एक करके हम क्या करेंगे, उस कंटेनर में मॉलिक्यूल छोड़ते जाएंगे, and they are ability to attract with each other, they are colliding with each other, and they form the sphere of influence. So the volume available for the first molecule, that is the V. Now the volume available for the first molecule is, that is the, for this one is for what? Not the first, that is the second one. By mistake I am writing the here first. So the volume of available for the second molecule is V minus 8x. Then what, 8x is nothing but, yes, that is the 8 4 by 3 pi r cube. So x is the, so we get V minus S. Then volume of available for nth molecules, that is V minus in bracket n minus 1 into S whole bracket closed. So by entering one by one volume, we get the average space available for each molecule, that is V plus V minus S plus V minus 2S and so on to up to V minus in bracket n minus 1 into S whole divided by n. by rearranging the equation, we get NV by N minus S by N, and we get the molecules for 1 plus 2 plus 3 plus up to N minus 1. Then by rearranging it, we get V minus S by N into N minus 1 by 2. So this equation gives the V minus Ns by 2 plus S by 2. Just simply rearrange this one. So here S by 2 can be neglected because as the number of molecules is very large, so S by 2 can be neglected. So what is the average space available of each molecule? That is V minus Ns by 2. Substitute the value of S, that is the V minus N into 8x by 2. Here, so 2 gets 8 get cancelled by 2, so it is a 4. So we get V minus 4 into Nx. So here 4 minus Nx is the B, and that is the 4 times the actual volume of this molecule, that is the B. So the van der Waals equation of state for a gas is here P plus A by V square. So for the correction of volume, that is the A by correction of the pressure, that is the A by V square. So P plus P. So as we know the real gas equation, PV is equal to RT. So for P we require the corrected pressure, that is the A by V square. So we get the P plus A by V square. Here V minus B, here this one, that V minus B is the correction due to the intermolecular of finite size of molecules. That is the van der Waals corrected equations, where A and B are the van der Waals constant. So this is the van der Waals equation of the state of gas. It is worthwhile to mention that the constants A and B depend upon temperature and volume. Since A by V square has the dimension of the pressure, hence the units of A are atmospheric pressure per centimeter raised to 6, and the B is centimeter cube. The values of A and B are usually quoted in gram molecule in CGS system. So this is the van der Waals equation. Now we can make the arrangement of P plus A by V square plus V minus B as per our requirement, and we discuss the van der Waals equation of state. Suppose P is equal to RT by V minus B minus A by V square. Just I am changing the position of A by V square minus or V minus B. So by substituting the proper values of A and B and R in the equation, one can obtain isothermals for gas of different constant temperature. And if we plot the isothermals for CO2 at the same temperature at which Andrews has done, so the isothermals would be in like Andrews experiment. Some liquefaction process is done. So at high temperatures, both the theoretical and experimental isothermals are similar, and there is a good agreement between the two. In both theoretical and experimental curves, the isothermals at 31.3 degrees centigrade has a point of inflection which represents the critical point P. What are the defects of van der Waals equation. It does not tell when the condensation starts. The values of constant A and B do not remain constant at all temperatures. If we calculate the values of critical constant, we observe that RT, that is the critical temperature, RTC divided by critical pressure, critical volume, is equal to 8 by 3 for all gases. But actually the values of RTC by PCVC varies with gas, and it has an average value of 3.77. The value of critical volume Vc is equal to 3B, whereas experimentally it is equals to TB. So this is the van der Waals equation. Van der Waals equation of a state for a gas. In next session we discuss on the what are the critical constant or estimation of the critical constant. So thank you very much for watching this video.